From ContainerDays Hamburg, this video is proudly presented by DAX IT.
Yeah, so today's session will be about ensuring high availability with global load balancing in Kubernetes. I just wanted to make it short. My name is Matthias Hauber. I'm a cloud architect at Prodyna. I'm based in Stuttgart doing Kubernetes, Azure all day. So that's my background from there. To start with the agenda, so we start my timer. About the motivation, why do we need global load balancing? What do the terms really mean? What can we achieve with that? Then the solutions, we will have a look at the requirements. What would be an ideal solution? What is out of scope? What doesn't make sense for our requirements to look at? Then the focus of this talk will be on KHGB. I also have a demo with that. Just 2 slides for the Azure services so we can somehow compare it. And that will be the last step here, the comparison between these tools. So because in the end, probably most of you will use some kind of provider. They will probably already have some kind of solution. And then you will ask yourself, okay, what should I use? Should I go with the open source CNCF version KHGB or with the cloud provider services? So let's start with the motivation. So first things, what is load balancing? So if you think of, you have your application, you have probably an endpoint for that, which is your ingress controller, for example, the load balancer. You have a domain, and then you have one endpoint. And now is the question, okay, if we want to have more than one endpoint, we need to have some kind of service in front of that to ensure that the user will be connected to the right endpoint. And for that, there are multiple methods to choose the right endpoints. And it comes from distributing the load among these endpoints. That's why it's called load balancing. But in the end, it ensures availability, reliability. There will be always a healthy endpoint, and performance. The users can connect, for example, to the closest endpoint. You can think of load balancing 2 types. If you think of the network layering, layer 4, which is just TCP, UDP, and there are layer 7 load balancers that are application aware, so HTTP, HTTPS traffic. So in the end, the client connects to our service, a load balancer, and the load balancer will either request or give back the right endpoint to the user or the client. And what does high availability mean? So that's what we're trying to achieve. So the goal is here to minimize the downtime or maximize the uptime. So our application is always accessible for our users. We don't want to have single points of failure there. So if one endpoint, we will see that one cluster is not available, is down, maybe some kind of region failure, for example, then we still want the user to be able to access our application. If we think of just Kubernetes, we have a lot of built-in high availability. If we think of pods, we have pod disruption budgets, we have pod topology spread constraints, we have health probes, we have all that mechanism to ensure the user always gets a right response from a healthy endpoint, which is in the end a container. Also, the control plane is redundant. We have redundant master nodes. We have mostly 3 times our Kubernetes components. So everything in Kubernetes is already built for high availability. Also, if you are, for example, in the cloud using a managed Kubernetes service, you can split the nodes across different availability zones, so different data centers. So even if there's some problem with power or something like that, you have at least some of your nodes there that Kubernetes can then shift the workload to. So our cluster itself is high available if we do all that, if we implement it. But what is missing if we think of entire clusters are gone. So for example, with a region failure, okay, if we spread it across multiple availability zones, even if the region is then not available, it doesn't help us with anything. So we want to achieve high availability for, in the end, the cluster and seeing the cluster as the endpoint. So here one world map. If you think of a user, that just tries to connect to some kind of domain, here app.domain.com. It will go probably to the nearest endpoint. We have a lot of Kubernetes clusters here. They're somehow connected. And if that Kubernetes cluster is not available anymore, it will just shift to another cluster and the user will connect to that endpoint. So, but for that, we need some kind of, or we need one endpoint, one domain to connect to, and then we need some kind of load balancing to get the right endpoint to the user. And that he can always or she can always access the application. So that's why we need global load balancing to achieve exactly that. If you have multiple clusters worldwide or region-wide to have some kind of load balancing in front. It's doing the same thing, just globally instead of within a region. So it's distributing traffic across the endpoints. Also, it ensures availability. Our application is always accessible, performance. So we always get, or the user always gets the nearest endpoint, the fastest response, and also built-in resilience. So regions can fail. There can be, I don't know if you heard it in the news, with the C cable from Azure and AWS in the Middle East. There can be some kind of routing problem for the worldwide traffic. Even with that, we then don't care because we have probably multiple or clusters in multiple regions. And there are two main approaches if you think of global load balancing. One is DNS-based. So a user just connects to a domain or tries to get the IP address to get the response from, and the DNS-based load balancer chooses the endpoint and just gives back the IP address, and the user directly connects to the endpoint. With a CDN, so a content delivery network, the users always connect to the nearest location of the CDN provider, and then the CDN provider will handle that request to the endpoint and then already give the answer back to the user. This allows also to do caching and stuff like that. If we have a look at, like a bit more visual. So in the first graph here, DNS-based load balancing, the user really connects directly to the endpoint that it then gets from the DNS-based load balancer. And with a CDN, it already gets the request back from the CDN provider. This allows to cache and do TLS termination and all that stuff we get from it. A hint already here, DNS-based load balancing is layer 4 because it just gives back the IP address. Doesn't matter which protocol the user in the end uses to access our endpoint. CDN-based load balancing is HTTP, HTTPS traffic. That's why we get web application firewall and all that stuff. There are multiple strategies, or how is in the end the load balancer selecting these endpoints. It could be very simple, active-active, all the endpoints are responding, can be round robin, so the traffic is split equally among all clusters, all endpoints. We can have weighted, so most of the traffic goes to cluster A and the rest to cluster B. We can have geographic, for example, if you have different data residency laws in the countries, we can say, okay, users from Germany need to connect to this endpoint, users from the UK to this endpoint, users from Switzerland need to connect to an endpoint within Switzerland. Also performance latency, so it just gives back the nearest endpoint and the user will connect to that endpoint with the usually lowest latency or the least network hops to reach the endpoint. Active-passive, that's also what my demo will be, is some kind of failover thing. So there's one active instance that is responding to all the traffic, and only if that primary endpoint will fail, the secondary endpoint or endpoints will then serve the traffic. So we have one primary, and then only in case of failure, the other endpoints will serve the traffic. So now we know, okay, what is global load balancing, why we may need it or may not need it. Now we can think of solutions for that. So what are our requirements? It should be vendor neutral and open source. That would be the best for us. The clusters should be independent. So if we use clusters or see them as the endpoints, they need to be independent. There should be no cluster-to-cluster connectivity needed, because then they are dependent. It should work. That would be also the best in any environment. Doesn't matter if it's on premises, cloud, public or private setup. There should be an automatic and fast failover if we use that active passive, and it should support all that load balancing strategies that I just mentioned. Also, it should have health checks. So the load balancer needs to know if that endpoint is healthy or not, or it will just give back a faulty endpoint, and then the client will get errors. So it needs to have some kind of health checks included. One solution that you may see if you Google like global load balancing is Cilium Cluster Mesh, but this has really another focus, because Cilium Cluster Mesh is focused on pods as the endpoints, and it tries to achieve high availability within the cluster. So if, for example, in this case here, these pods of the cluster on the right are down, it will fail over, and the service will distribute the request inside Kubernetes to the pods in another cluster. So clusters are dependent, they are connected to each other. We don't want to have that, because if one cluster goes down, still we don't have one endpoint or one load balancing where we can connect to. So it's not really helping us here. Before I will show you the open source version, KHGP, just 2 slides about the Azure services, because then we can compare it a bit. That's also what I'm using in the end to compare to. In Azure, we have the Traffic Manager, which is a DNS-based load balancer. It's really simple service. We have endpoints, and the user can connect to this Azure Traffic Manager domain, and they will get back the IP address for one of these endpoints. We have health checks. We have all that load balancing strategies, really simple to use. Endpoints can be everything. So domain, IP addresses, Azure services, outside, inside of Azure, doesn't matter. It's just giving back the right IP address. CDN-based load balancers, there are a lot. There's like Akamai, there's Cloudflare from Azure, AWS, Google, whatever you want to choose. In Azure, it's called Front Door. It only, like almost all, or I think all CDNs, it can only handle HTTP, HTTPS traffic. It uses Anycast, because if you think, okay, I need that one IP address where the user connects to, because I'm not directing the user to different endpoints, I'm doing the request already for the user. So it needs to connect to one IP address. And for that, it uses Anycast, which just means we can have multiple endpoints in the end here, the Azure Front Door edge locations where the user can connect to. And then the CDN provider here, Front Door, will take care of getting the answer, the response from the endpoints. We'll get that to the user back, and it will do caching, web application firewall, all that nice layer 7 stuff. Also, it uses things like split TCP, which means it keeps like a short-lived connection to the user and a long-lived connection across requests to the endpoint. So it already saves some time, when traveling or doing the handshake and stuff like that. So it also helps with performance here. Now to K8GB, hard to pronounce. It's an open source tool. It's also cloud native tool. It's leveraging CNCF projects like core DNS and external DNS. It can provide us with that high availability across multiple Kubernetes clusters. And these clusters can be in other regions. Then we will have global load balancing. We don't need any control cluster or something like that. It supports almost all load balancing strategies except for performance and latency. That's not possible because you need to calculate like the latency and network hops and stuff like that. But all the other strategies are supported. Health checks are actually based on pod health probes. So if there are no endpoints for the service within Kubernetes, then also it knows that, okay, the cluster is down, I will shift, or this is what I will show, fail over to another cluster. It currently only works with Ingress, so no gateway API support here. This means it only works with HTTP, HTTPS traffic here. But it's a DNS-based solution, so it could handle also layer 4 or do that because it's just giving back the IP address, but it works with annotating ingress objects. So the main component is the controller of KHTP. In the end, we have some kind of provider where our root domain lives. That's here called, or in the docs called Edge DNS. We will delegate a zone to the core DNS, which is running inside the cluster. And all this controller is doing, it watches for GSLB objects. That's just the CRD for KHTP, Global Server Load Balancing. Or if you don't want to create it on your own, you can just annotate the ingress, and then it will automatically create that object. Then it will check, okay, are there pods? Is it possible to reach pods? Does the service have endpoint? And then it will just create DNS endpoint objects, and with that, core DNS will update its records. So it's really only doing that. Now we have multiple clusters, multiple KHTP instances, so we need to install the Helm chart on each cluster, and it somehow needs to connect. So it's connecting always to the core DNS of the other cluster and is getting like the locations from the other cluster that are healthy. So it syncs also with all the instances. By default, every 30 seconds, we can set it down or up. But that's everything the controller is doing. If you have a look at the object, so the ingress, I'm just adding here two annotations, which is I'm using the strategy failover, and what is my primary cluster, so the cluster that will always respond, or, only if there's a failure, it will fail over to the other cluster, and then it will automatically create that GSLB object that is just referencing here the ingress and has the strategy written inside. So how it works, we have core DNS in every cluster. That's where are all the DNS records stored. This core DNS is exposed publicly. So it's not the core DNS of your cluster, it's another core DNS instance. This will be either exposed directly via the load balancer, or you can also expose it with ingress controller. For example, Nginx can do that with config map and just forwarding traffic from other ports or other protocols as well. So UDP 53. It uses also external DNS. That's how it can make that domain delegation. So if a user accesses our application, it will direct the search for the right IP address for the domain the user enters. It will delegate that to the core DNS of the cluster. And these entries are done by external DNS. I will also show it in the demo, then it gets more clear. Here also from the KHTP docs. If you think of, you have here cloudexample.com. In this case, it's AWS Route 53 what is used. I will use Azure DNS. You can use everything, Cloudflare, Infoblocks, whatever. Just needs to be some kind of DNS provider, which external DNS can enter the records. And then there will be here step 1, zone delegation. So we have, in this case, two clusters. One is EU, one is US. And it will just delegate a subdomain or a zone to core DNS. In this case, you see it here a bit more smaller. Here, it's app cloud example.com, so it's a subdomain from that, and it will say, okay, if you are looking for an IP address for one of these domains, please ask either this core DNS or this. So we can enter multiple, and DNS is just done like that. If the client tries to connect and one is not available, just will take the other name server to resolve this IP address. So that's how, it doesn't matter if it's cluster 1, cluster A or cluster B answering, and also they are syncing between each other. That's what the KHTP controller is doing. It's doing that sync and getting from the other core DNS all the records. And then just we create DNS endpoint objects here to update the core DNS records. Watches for this GSLB object, and that's already it. For each cluster, we will also have one A record in our Edge DNS. So there will be one NS record, the delegation, and for each instance an A record, which is just pointing to the core DNS IP address, so how it can be reached because it needs to sync, so it needs to know how to reach the other instances. How to set up and install it, just a Helm chart. There are examples for all DNS providers. We can have multiple load balance zones. They did it in the new version, which came out in July. So before it was only one zone per instance, but now we can specify also multiple zones. The cluster geotags, that's just the name, how an instance is called in KHTP, which can be a region, for example, need to be specified beforehand. Also, when a new cluster will join, we need to always Helm upgrade install the all the Helm charts across all clusters, because you will see it here. That's the values that I used for the demo. Here's an external GSLB cluster geotags. That's a comma-separated list from all the other instances, because it needs to synchronize, and we need to tell him or tell KHTP where to look for. And it does this by resolving these A records, by the naming pattern, and then can connect to the other clusters. But if we want to add a cluster, we need to upgrade the Helm chart on all instances. So that's the biggest downside of KHTP. In the end, you just specify the zones here. I'm using here CD25 K8STCC, just a demo domain, and I will delegate this demo dot from that root domain to KHTP, and it will handle the traffic for that. And now we come to the demo. So I have two clusters. One is in Germany West Central. I need to. Why is it not showing? I think if I close it, now it's showing. I have two clusters. I have K9S, which is starting now for both. I have here my current IP address and the current cluster that is responding, and my script will now just scale down the primary. So it will scale down the, here in this case, just a pod info deployment. It will delete the pod, and then my cluster, now you see it's deleted, my cluster is down, it cannot be reached anymore, there are no pods available, and we will see that it will just fail over to the other cluster. Takes some time because it needs to synchronize, and there's DNS TTL, but you already see it now. The one in the East US is responding to our client's requests. If you have a look in the browser, you will see that now for this primary Germany West Central, it's not reachable, and even if you reload it, that's the caching of the DNS. Now it worked. It takes some time until the user will connect to the new endpoint, because this DNS request is cached. But now it's East US, and if I'm just doing, now I will scale it up again, and then we will see it will switch back to the primary, because it's the one that should handle the traffic if it's available. So the pod now started, now it will synchronize, and then it will be Germany West Central again. Let's just wait for that. Now it's Germany West Central again, and I will still see the other endpoint here. Again, it will take some time until the DNS cache is emptied, and also the browser is caching, the operating system is caching, the resolver, for example, your router, Fritzbox router, whatever is caching. So it takes some time. So that's the downside of DNS-based load balancing. So now I have here Azure. This is the domain which I'm using for the cluster here. In the end, there are only 3 entries that are relevant. There's this NS record, so name server. It's just delegating the zone demo, which I'm using here, podinfo.demo. Just delegating that to the core DNS instances of the clusters. So here, that's the domain for that. And here, the domain, we have the 2 A records that are pointing to our load balancer where core DNS is accessible. And that's everything it does. The client connects to it, is looking for the domain name. then it will be forwarded to core DNS or will query core DNS, and that's how it knows where to connect to. Now to the comparison of the solutions. So what to use for which use case? We saw there's like KHTP, which is the open source variant. We have CDNs like Cloudflare, Akamai, Azure, whatever, and DNS-based load balancing. So they can all serve layer 7 traffic, HTTP, HTTPS. The layer 4 traffic, a CDN cannot handle. KHTP at the moment cannot handle because there's no support for gateway API. So only a DNS-based version, like of a cloud provider, for example, can handle that. Open source, of course, it's only KHTP. Health checks, all of the services, all of the solutions have KHTP. It's based on pod health. The CDN and the DNS-based one, we can just specify some kind of health checks. For example, that path and that port and so on. And it will just check regularly if the endpoint will respond with an HTTP code, etc. And the health checks from KHTP, that's why it's nice. We have also exec, right? So for a database, we don't have an HTTP endpoint, so we can leverage that exec health probe. Supported load balancing strategies. KHTP can do everything except for performance latency, because that's where you need really the like the global setup. You need to have all the tables, which endpoint connects to which IP address in which time, and so on. That's what the CDN provider is generating for us. So that doesn't work with KHTP. If you want to have that, then the CDN is probably the best solution, will be the most performant. Also, the failover will be faster because there's no DNS TTL, because it's not DNS-based, it's anycast. You get one IP address, it always connects to the same, so it will fail over faster. And the DNS-based, it supports everything. It's really simple. Also layer 4 traffic. Only the DNS TTL can be a problem here. So we need to wait, or the user will see for some minutes some kind of error. What is the downside of KHTP? We need to really upgrade on all instances if we want to add a new cluster. So that's the biggest downside. What good is it works in private setup, so we can set up a bind. We can use a domain server from Microsoft, etc. So it doesn't need to be public in the cloud, which my demo was. It can also be on the private setup. So the use cases for KHTP is availability. So we can do failover, we can do active-active, like weighted, we can do round robin, just spread it across all endpoints. Also legal requirements. For example, if you have data residency laws, you can say users from Germany will connect to this endpoint and so on. We can specify that in a table. And the CDN-based one is good for latency and performance, also for availability. And we have all the nice layer 7 features like replication firewall, caching, TLS termination, and so on. Also route-based, traffic distribution, all the nice features, and DNS-based. It is actually for all use cases. Availability, if you have the DNS TTL, it's actually not that nice because the user will still see some errors when it's doing the failover because of caching. What are the challenges if we speak about multi-cluster, which is in the end what we want to achieve, multiple endpoints, multiple clusters. So we need to we have a lot of operational complexity. We need to maintain Helm charts, all the stuff, version upgrades, and so on. Observability. We need to have some kind of monitoring across all the clusters. So we need to set up everything. Also data management and state. So if we have a database inside our cluster, we will need some kind of replication, the database needs to support it, or we need to use of a cloud provider that also has more than one regional endpoint. So we have like that global scale. So these are the challenges. Then thanks for attending the was too fast. Thanks for attending the session. We also have a booth. If you want to win something, there's like a Lego Milky Way set, so Galaxy set. You can win that and just scan a QR code and fill that out. And now we are at the end, and I'm happy to answer any questions. Is GUID implemented in KHDB, or it's using DNS provider features? No, it's implemented in it, so it's using core DNS. There are core DNS plugins which can handle that. It's just taking like a table. It's a bit more difficult to set that up, but it's really in KHTP. So the DNS provider is just there for the delegation in the end. It's working directly with K8S, load balancer service resource, and log to how it manages ingress resource on the roadmap for KHTP. I'm not sure what means working directly with load balancer service. So I don't know if the core DNS exposure is the question here. You can either do it with an ingress controller, like with a config map, Nginx, or really use a load balancer. I hope that answers the questions. If not, you can also come to me later. And KHDB would have the same TTL drawback as the pure DNS-based solution. Yeah, so that's exactly the same. Also, it has that reconciliation loop between the instances. So also that takes time, and if a cluster goes down, it has exactly the same caching problem.
Do the last one as well.
How to mitigate DNS TTL problems? What are cons of setting lower value for TTL? In the end, do you want more requests? So the users are always asking your endpoints, and you pay for requests that you are answering. For example, in Azure, it's like 50 cents per 1 million request. It's not that much, but still that's the downside. Always request sending to get the IP address. And if you set it lower, then of course the failover will be faster. Well, that's the pro. So we need to balance that. Then I think that's it.
Applause for Matthias. Thank you so much.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.